the antenna miniaturization. Because if you see nowadays, all the wireless communication devices, okay, starting from your Bluetooth device, your mobile, and all this stuff, okay, whatever you are seeing, the 5G devices, all these devices, if you go back 10 years, 15 years back, okay, if you see a Nokia mobile, okay, we used to use on those days, 10, 15 years ago, the Nokia mobile, the big one, hardy ones, okay, and in that mobile only we have GSM band, okay, either 900 megahertz or 1800 megahertz. We don't have the internet, okay, and we don't have the Bluetooth. I mean that kind of features on those days, okay. But nowadays you see the antenna provide. I mean nowadays the mobile phones are more smart, okay. Smart means not only we are talking, okay, we are using video calls, okay, internet, Wi-Fi, 5G, and so many things. Okay, so the one of the major component of these devices is the antenna. Okay, and antenna is one of the most important things in these devices, as well as antenna is the culprit in these devices. Why I'm saying it is culprit? Because it takes lot of physical space. Okay, in antenna, I mean in mobile phone, it can take lot of physical space. So that is why the topic antenna miniaturization is so important. Okay, and it is so hot topic nowadays, because in a small devices, okay, like a Bluetooth devices, you see that it is a very smaller than a pen drive nowadays. Okay, so on those devices you have to fit an antenna. So how much small it should be, because not only antenna will be there, some other component ICs and some other circuit boards will be there. So that is why the antenna miniaturization nowadays is so demanding topic. And the second is the conformal antennas. Basically, conformal antennas are those antennas. For example, we have some existing structures. Okay, so how can we use those existing structure as an antenna? For example, uh, you have seen the conical front of a uh, racing car, or conical front of a missile, or conical front of a aircraft. Okay, so these are the made of metals. Okay, so how this existing structure can be used as an antenna? Okay, will not use any additional material or any additional metallic structure, but using the existing structure, how can we use those structure as an antenna? Okay, so these are my second topic. So starting with antenna miniaturizations. So basically what we have done here is that different type of antenna so far we have fabricated. In the left hand side, you see some slot kind of antennas are there. Okay, so basically these are the we have applied different technique of antenna miniaturization. Before
Well,
going to
excuse
the
me.
antenna miniaturization, what technique we have applied?
Yeah. Hello,
Yes,
sir.
yes.
Sir,
So
actually,
there's yes, yes.
is this your second slide? I think. Actually, till now it was confined to the first slide, where the title of the session is mentioned.
Oh, so that is a delay. I think some
Uh, I think that, sir,
actually
actually,
lag in the net speed.
actually, then, that is your voice is not matching with the slide, and this the second slide is appeared after the first one.
So just appear. So I have to wait. This is taking too much time actually. Now it is appear.
So now it is appeared. Now it is appeared, sir.
Oh, okay. So it's taking time. So I have to wait a little bit. Okay. So the antenna which we have been designed, okay. So antenna can be miniaturized in many process, okay. So conventional process are that we have to increase the length of the antenna, okay, by using metal, using spiral, or whatever way you have to increase the length, okay. And second thing is that either using inductive loading or capacitive loading. And third thing is the use of metamaterial. Okay. So these are the commonly used technique for antenna miniaturizations. So you see the in left hand side we have used four antennas. Okay, these are the antenna miniaturization, and on the right hand side there are two antennas. Okay, those are the conical conformal antennas. So first discuss about the miniaturized antennas. Okay, so in those antennas we have used either inductive loading or capacitive loading. So why we have not used the meander lines, or why don't you use the coils type of structure or spiral structures? Because if we use the spiral structure or coil kind of structures, these are made of metals. Okay, though the antenna will be miniaturized, but what will happen is that as because you are using more conductors, so conductor loss will be more. Okay, so as our loss is increasing, our efficiency will decrease. So as a result, when as a antenna engineer, we want efficient antennas. Okay, so efficiency should be 80%, 90% in that range. So that is why the antenna which we have been designed, okay, we have not used any spiral kind of structure. You see here a simple dipole antenna. Okay, a simple dipole antenna is loaded with two loop. Okay, only two loop instead of coil kind of structure or spiral kind of structures. We have used only single loop. Okay, as a result of that, the single loop, we have got uh, at least 27% miniaturization by using just using two metal uh, kind of metal loop structure. Okay, so why we are studying this thing, where we will use this kind of antennas? You see the application of antennas designed by us. One is the definitely the mobile, another one is the laptops, iPod, all these devices, because we can use straight away these antennas. Second application is that is our very interesting biomedical applications. Okay, you see that nowadays um, uh, endoscopic capsule. Okay, we are use endoscopic capsule. Some noise is coming. Hello, some noise is. Nowadays we are using the endoscopic capsule. Okay, so what happens is that our internal track. Okay, if something is damaged in our internal track, okay, intestine. Okay, so how we will detect? Because from outside we cannot see the what is happening in the inside. Okay, so what happens is that the doctor gives us some capsule. Okay, so that capsule travels in that spiral kind of our intestine and take the capture the photos and transmit to the receiver, and we see and analyze those things. Now in that device there is part antenna. Okay, so can you imagine that capsule is how small a capsule, okay, which we take when we get poor, I mean unhealthy, that times we take. So in that small capsule we have to fit a small antenna. Okay, so another application is that we are trying to design one kind of antenna so that it can be fit on that capsule. And the third type of antenna which I have described you is that conformal conical antenna. Okay, so as I told you, you see that in the spacecraft or missile nose, it can be implemented on those things. So I'm going to the next slide. Whether it is visible or not, I don't know. So please, I'm waiting, and please say, Dr. Oniban, please mention whether it is visible to you. My third slide.
Yeah, yeah. So now it is visible to you. Now it is visible. I'm
Okay.
requesting the participants. The participants also feel that the slide is visible or not, right?
Okay. Okay. So this is a actually this is an interesting kind of things. Okay, that what our research team trying to do, that we want to create a startup company. Okay, so the website is already launched, that is antmdu.com. Okay, so in that startup company we are launching our products. Okay, if you visit that website, you will find our product, though it is in the initial stage. Okay, we are upgrading that website. Okay, very soon you will get the full website. Okay, so this is another kind of things we are trying to develop. I'm going to the next page, 4th page. The basic things of antenna miniaturizations. So please, whether my page number 4 is available or not, Dr. Oniban, please,
Yeah.
if you,
So I can see it is
it
available.
is
Acha, Mr. Obirup, it is available.
Yes, sir.
Okay.
Yes, sir.
So
It's
each and
available,
every
sir.
slide, kindly speak out. Okay. Okay.
Okay. Okay, sir.
thank you. Okay, so now the, what is antenna miniaturization? Okay, how we will do that? I have already discussed that how can we miniaturize antennas. Okay, I told you that by using spiral kind of structure, or by using the increasing the path length of the antenna, or by using inductive loading or capacitive loading, or by using metamaterial. Okay, so basically whatever we do, there is two process of antenna miniaturization. There is case 1 and case 2. In the case 1, okay, you see that the length of the antenna is L, and it resonates at frequency 2 gigahertz. Okay, now keeping the same length L, okay, let's say L is 20 millimeters. Okay, keeping the same 20 millimeter, if the antenna resonate at 1 gigahertz, then we'll say that the antenna is miniaturized. Why? Because lambda is inversely proportional to the f. Okay, if f decreases, L will increase, right? If f decreases, L will increase. So you see that when my frequency decrease from 2 gigahertz to 1 gigahertz, my antenna length should increase. But instead of increasing, if we able to keep the same length, then it will be said that our antenna is miniaturized. This is one process. Second process is that case 2. Suppose our antenna length is L1, let's say 20 millimeters, okay, which resonate at, let's say, 2 gigahertz. Okay, now the antenna length is less than, let's say, 10 millimeters. Okay, half. Still, it is resonate at 2 gigahertz. Okay, then it will be said that our antenna is miniaturized. Why? Because even though our length is decreasing, from length is decreasing, so f should increase. But instead of increasing f, it is remain at 2 gigahertz, because f and L are inversely proportional. So this is the basic concept, nothing else. Just applying this concept, whatever antenna miniaturization we have got, we have just applied these two formulations. I'm going to the next page. Problems in antenna miniaturizations. I hope that it is visible to you. So what kind of
Yes, sir.
problem
Yes.
in yes, what kind of problem in general take place when we are doing the antenna miniaturizations? First thing is that as the size of an antenna is reduced, its performance suffers. Number one, efficiency decreases. Number two, quality factor increases. Okay, as our antenna is decreasing, okay, getting smaller, okay, so it does not radiate. Okay, as it is does not radiate means what? It stores more energy. Okay, when a structure store more energy, that means its quality factor is very high. The bandwidth decreases. Okay, because quality factors and bandwidth are inversely proportional. Okay, the bandwidth is inversely proportional to quality factors. Okay, so quality factor increasing, the bandwidth decreasing, and input resistance also changes. Okay, in generally You see smaller antennas has very low resistance, point 1 ohm, point 3 ohm, in that range. Okay, very small resistance. You see in Balani's book, if you see the input impedance of a loop around 3.315 ohm approximately. Okay, in that range. So basically it is very small. Okay, and dipole I think 0.75 ohm approximately. So as because the input impedance of that antenna, if it is zero point 0.7 ohm, 0.75 ohms, so when you will give some power with your cables, okay, cable have characteristics impedance of 50 ohms. Okay, so this 50 ohm will not match to the 0.7 ohm. So whatever power you will give to this antenna will not radiate. Okay, reflect back. So coming to the next page. So some of the novel aspect what we have designed in our antennas. Okay, so the antenna which we have designed basically. So first thing is the simplicity of the fabrications. Okay, all these antennas can be fabricated very easily. Yeah.
Yes, sir, it is
Second thing
visible,
is
sir.
that reduction. Yeah, thank you. Thank you. Reduction of the conductor loss, which leads to increase in the efficiency of the antenna. Okay, as I told you, in all our antennas, we are not using any kind of metallic coil or spiral structures. Okay, so as a result, what happens is that our conductor loss is very less. As our conductor loss is very less, our efficiency increases. Okay, in many antennas we have got 90%, 95% uh, radiation efficiency. Realization of a electrically small antenna and approaching it to the chu limit. Okay, this is very interesting thing. What is electrically small antenna and chu limit? Okay, so basically sometimes people confuse what is miniaturized antenna and electrically small antenna. These are the two different things. Okay, so what is electrically small antenna is that some definition is there, mathematical definition is that if k multiplied by k is the wave number, a is the, I'm speaking, k into a less than equal to 1, if this condition is satisfied by any antenna, then we can say that that antenna is electrically small. And what is A? A is the radius of a sphere in which we can enclose the antenna. Okay, that means A is the minimum radius in which the antenna can be enclosed in a sphere. Okay, so our k into a, if we multiply, okay, k into a, and if the value is come less than equal to 1, that then we can say that our antenna is electrically small. Okay, and what is chu limit? Okay, chu limit, chu is a scientist who invented some limit. Okay, so that limit is called chu limit. Okay, so q chu, okay, quality factor q chu is mathematically defined as, I think I have not written here, 1 by k plus 1 by k cube. Okay, q chu is called q chu equals to 1 by k plus 1 by k cube. This is the mathematical expressions. Next thing is that I have already mentioned miniaturization, avoiding coil conductor or helical structure which potentially increase efficiency. In our case, very close to electrically small limit, we have got 0.58 for loop loaded miniaturized monopole and 1.04 for loop loaded miniaturized dipole antennas. Next things, what is the advantage? We have not used any additional matching network. In many cases, we have seen that as because the antenna we have designed, now when we are giving some power, after providing the power, we see that our antenna is not radiating properly. Then we have to match the antenna. Okay, how we'll use the quarter wavelength and balloon kind of structures. Okay, so then in that case we have to use the additional matching networks. Okay, which will be costly. Okay, so in our case, as because our efficiency is very high, so we do not need any additional matching networks. Third thing is that release of, as because our antenna is miniature, release the ground plane area above the slot for accommodating electronic circuit and effectively reduces the antenna size of the slit-loaded miniaturized configuration. Next, a significant reduction in resonance frequency is achieved. I'm going to the next slide. This is another when you will design an antenna. Okay, when you will design an antenna, this is CPW line calculator. You may be familiar with these things. Okay, because when you are designing any kind of antenna, either it is slot antenna fed by microstrip line, slot antenna fed by CPW line, or a microstrip antenna fed by different type of strip line. Okay, what you have to do, you have to design the CPW line in a such a way that it matches. Okay, matching is very important, because suppose if I design, we can design any antennas, but when we'll see from input side, okay, when we'll see from the input side, the input impedance of that antenna, okay, that is in that case the value of the resistance should be close to 50 ohm. Okay, so how will do that? How can you know that it will be close to 50 ohms? Okay, so that is why this kind of calculator is available. Here I have just shown you a CPW line calculator. There is also a microstrip line calculator also there. So just giving that value epsilon, the trace width, okay, you can see that trace width is W, and the ground plane separation S is there, and the thickness of the substrate. Okay, if you put this value, then you can calculate that Z naught. That is our characteristics impedance. So I have chosen one of my antennas in which the Z naught value is 49.94. Okay, so when you will design your antennas, you have to keep in mind all these things, so that after designing your antenna, you don't have to use any additional networks. Okay, coming to the next page. So what is the advantage of CPW feed? Okay, over microstrip feed? Okay, low loss compared to microstrip feed.
And your slide. Yes,
Second
sir. Yes.
thing,
Okay.
yes,
Okay.
no,
Yes,
now
sir.
visible. Okay, thank you. Okay, I'm extremely sorry that my network is not working properly.
Sir,
It's
I
okay.
have a question.
Achha,
Can I
advantages
ask
of
you, sir?
hey,
With respect to the previous
yes,
slide which you showed,
yes,
sir, the CPW calculation, sir, actually this
okay,
CPW calculator,
okay.
we can get it in which simulation software, sir?
No, not this software. I mean, it is an online software. Okay,
Okay,
that is microwave. You can just search in the Google microwave 101.
okay, sir.
In Google, just search microwave 101 CPW
Okay,
line calculator. It will automatically come.
okay. It is an online
Okay, if you have a
calculation
mobile,
platform.
it is, yes, online application, calculation calculator.
Okay, okay,
Okay,
okay. Thank you,
and
sir.
the software, I mean, there is defined. Okay. Next is the advantages of CPW feed. So I think it will take again some time, I think. Whether my page is available, advantages of CPW feed.
No, no.
Please, Dr. Anirban Karmakar, if you're there. Okay, just I'm waiting then. Okay.
Oh, okay, sir. Yes, sir. Hello.
Yes, sir.
Yes, sir. It is visible.
Now it is available.
Yes, sir. Yes, sir.
Okay. So yes, okay, I'm continuing. So advantages of the CPW feed. Okay. So advantage means obviously when we're talking advantage with respect to, I mean, in which, so advantage of CPW feed over microstrip feed. Okay. Low loss compared to microstrip feed. Okay. In microstrip feed, we are using the metal structures. Okay. The field is flowing through a metal structures, or current is flowing through a metal structure, and that metal structure is radiating. Okay. So as because that metal structure is radiating, obviously there will be some loss. But in CPW, okay, the field is propagating up through the metal. Okay, in that I mean non-metal regions. Okay, that is why loss is less. Second point is the uniplanar configurations. Okay, both ground and our power supply, because coaxial connector has 2 points. One is the ground, another one is the power. Okay, so both those contacts are on the same plan. So that is why it is called uniplanar configurations. Number three, avoid drilling antennas as required with coaxial feed. If you feeding with coaxial, so we need to drill the antennas, okay, which is very difficult, okay, and also that after that you have to solder, okay. So that is also if you use some adverse kind of situation, the solder may come out, okay. So it is better to use CPW line fed, and do not need any vias, okay. We do not need any vias in their structures, okay. Different kind of CPW feed. Okay, first one is that you see inductive feed. Second one is called capacitive feed. Third one is square loop feed, and fourth one is the circular feed. So these are the four type of feed. Basically, 1, 2 is the main. Okay, then after that, uh, circular, rectangular, triangular, and all these things took place. So
Hello, sir.
I'm coming, going to the next page. Yes, yes,
Sir,
yes.
there is a question, sir. Sir, which one among them is the most efficient? You would say?
That feed.
Yes, sir. Yes, sir.
So it depends upon that. The antenna which design. Okay, efficient in the sense. Okay, your antenna is efficient. Okay, in a sense. For example, if we use inductive feedings or capacitive feedings. Okay, the thing is that now you have a DRA kind of structures. Okay.
Okay.
Now the DRA has different mode. Okay, different resonating mode. Okay, so we have to excite exactly the same mode using this kind of feed. Either it can be done with inductive feed or it can be done with capacitive feed. So it depends upon the in which mode you are exciting. Okay, it is not like that your inductive feed is more efficient compared to the capacitive feed, or capacitive feed is more efficient in terms of the inductive feed. How
Okay.
you are, how your energy from this feed is how coupling to that dielectric materials. Okay, you have
Okay.
to see that those things. Okay, if it is coupled properly, then it will radiate properly. Okay, if it is not matching, then there will be some losses. Okay, as a result, your efficiency will decrease.
So the sir, efficiency of the structures depend on the modes actually.
If you use the dielectric kind of structure,
Yes, sir.
okay, if you use the dielectric kind of structure, okay, so in that dielectric there is some different modes are there.
Yes, sir.
Okay,
Right, sir.
so all these modes are not if you excite particular mode will radiate properly.
Yes,
Okay,
sir.
so as a result, you have to give energy in such a way that exactly that mode excite. If it is not excite, then energy will be lost. It will store the energy. Instead of radiating energy, the dielectric material will store the energy.
Okay. Okay. Okay,
Right?
sir. Okay, sir. Okay, sir.
Okay, I'm coming to the next slide.
Sure, sir. Sure, sir.
Okay. I think whether it is
Yes, sir.
visible or not, I'm not
Visible, sir.
sure.
Visible, sir.
I'm taking some time. It is visible, no?
Yes, sir.
Okay. Okay, so this is one of the antenna which we have, one of my research scholar has been designed. Okay. So what we have done is that instead of taking the CPW feed, here we have used the microstrip feed. Okay. So he has done these things. Okay. So here the slot length is taken 20 millimeters. Okay, the substrate is used RTEIT, okay, 6010 LM. Okay, it is very costly materials. Okay, and the height of this material H is 2.54 millimeters, and the permittivity of this material is 10.2. So the length of this slot you see is 20 millimeter, and width of this slot is 1.2 millimeters, and it resonates approximately 2.27 gigahertz, and the minus 10 dB impedance bandwidth is 3.72. So you can see it is very narrow, but the efficiency is very high. You see 95%. Now we are miniaturizing this antenna. Coming to the next slide. Okay, you see my next page is visible. Reduction in resonance frequency.
No, not yet, sir. Not yet.
Not yet, sir.
Okay, I'm waiting. Okay, I'm waiting.
Yes, sir.
Yes, sir.
Yes.
Now it is visible.
Okay, thank you. So basically, you see, we have used two loop. Okay, these are the loop. I mean, not metallic loop. Okay, these are the slot kind of loop. Okay, this is non-metallic loop. But you see the length L here, L SL. The total slot length is 20 millimeter here. I have not changed the length. I have kept the same length, and in that antenna, what I have added, we have added two slot loop on both side of that radiating slot. Okay, which have the diameter D1 and D2. Okay, so using this loop kind of structure, our antenna, I mean our resonant frequency reduced to 1.60 gigahertz. You see 1.60 gigahertz below that. Okay, so from 2.27 gigahertz to 1.60 gigahertz, in terms of percentage, we are getting 29.51 percentage of miniaturizations, and our minus 10 dB bandwidth also increases. That is 6.75. So improvement is around 81%. And in spite of loading, okay, in spite of loading, our efficiency is more than 90%, 93.54. On the right hand side, we have shown both the loaded antenna resonance frequency and unloaded antenna resonance frequency. The unloaded resonance frequency is 2.27 and the loaded one is 1.60 gigahertz. So not only the simulated results, we have shown the measured results also because we have fabricated these antennas. Coming to the next slide. So next slide is the input impedance plot. I think it is not visible. I think I have to wait.
Yes, sir. Not visible yet, sir.
Okay, I'm waiting.
Yes, sir. Visible now, sir.
Okay, this is the input impedance plot. The input impedance plot of the unloaded antenna as well as loaded antenna. Okay, so the reactance curve. This is the reactance curve. Okay, this is the reactance curve. I'm trying to show with my pointers. Okay, this is the reactance curve of a unloaded antenna. Okay, this is the reactance curve of an unloaded antenna, and in that point the reactance is 0. Okay, in that point the reactance is 0. Definitely at resonant frequency point, resonant frequency point, our reactance should be 0 and resistance should be equals to 50 ohm. Okay, so here at 2.27 gigahertz, our reactance curve is 0 and our resistance curve, the value is approximately 50 ohms. The interesting thing is that if you follow this reactance curve, okay, just coming to the left hand side at around 1.6 gigahertz, okay, at 1.6 gigahertz, you see the from the arrow at 1.6 gigahertz, you see this much amount of capacitance we have to cancel out. If we able to cancel out this much amount of capacitance with the help of that loop, actually any loop provides us inductance. Okay, so that loop, two on the left side and two on the right side, providing us inductive loadings, and those loadings are cancelling out this capacitance. Okay, so this much capacitance is cancelled out. As a result, this dotted line is the reactance curve of loaded antenna, which passes through 1.60 gigahertz. Okay, so this is the concept. Okay, just we are cancelling out the reactance with the help of, if we have capacitive reactance, we have to cancel it with inductive. If we have inductive reactance, we have to cancel with capacitive. Coming to the next page, I'm waiting. I think it will take some time. One side lit, another side is low.
Yes, sir, it is visible.
Okay, so this is another kind of structure. Instead of taking loop on the both side, we have kept loop one side, and another side, instead of loop, we have used slit. Okay, slit has length of lambda g by 4. Okay, any slit which has length less than lambda g by 4, it offer inductance. Okay, from transmission line theory, we know that any slot which is the length lambda g by 4, it will offer inductance. Okay, from that formula. Okay, that is why Zn equals to ZL plus Z0 ZL J10 beta L. Okay, that formula. From that formula, we are getting the inductance. So by using this these two type of structure, our resonance frequency reduced further. It is now 1.37. Previously it was 1.6. Now it was 1.37. So we are getting more miniaturization. You see 39.64, but our efficiency also again 94%. So these are the return loss plot we have shown, loaded and unloaded. Coming to the next page, I think it will take some time, so I'm waiting.
Yes, sir, visible.
Visible.
Okay, this is the same structure what we have used previously. Okay, so instead we have what we have added additionally is that you see some dotted line is there. Okay, these are not slit, these are the strip bottom of the substrate. Okay, these are the strip on the bottom of the substrate. If you see the fabricated antenna right hand side, okay, on that right hand side you see slit on the top, left hand side is the slit. Okay, these are not metallic structure, and right hand side is the loop. And uh, this is the top view, and the bottom view is showing you the microstrip line and the uh, metallic strip. These are the metallic strip. So dotted line what we are showing here is the metallic strip. So this is third design. Using this design, our resonance frequency reduced to further reduce. It is now 1.18. Okay, as a result we are getting more miniaturization, 48%. But you see that previously we have got the efficiency around more than 94%. Here our efficiency little bit decreased, as because we are using little bit conductor here, this strip. Okay, metallic strip. So our efficiency decreases little bit. So this is one of the structure. Okay, so just using these structures we are getting this. Coming to the next page, just a minute. So I'm waiting. Okay.
Sir, which simulator you have used for this paper, sir?
Pardon me, which simulation
So
software?
simulate. Yes, sir.
Simulation HFSS, ANSYS HFSS.
Okay, okay, sir. Okay, sir. So your
Hello.
next slide is visible.
Okay, so we have the license version. Yeah. So this is a kind of structures, okay, in which we have tried to use it in wireless communication applications. Okay. So design of miniatures antennas and bandwidth enhancement for wireless communications. So here we have taken different slot length. Okay. Slot length is 20 millimeters. Okay. But the material is different. Yes, the material is different. Okay, the material is we have taken is FR4. Okay, instead of RT2 red, we have taken FR4 here. So the resonance frequency here we have got 3.29 gigahertz. Now my next slide is visible.
Yes, sir.
Yes, sir. Visible, sir.
Okay. Yes. So I'm just discussing these things. This is a very similar type of that kind of work. Instead of RT2 rate, we have used the FR4 because, as I told you, the RT2 rate is very costly. So what we are trying here is that instead of actually taking the RT2 rate, we are using the FR4, and we have designed, try to the slit length and all these things we have adjusted in such a way that we can get different kind of communication band. Okay, so just by using that things we have miniaturized this antenna. Okay, so just using this kind of miniaturization technique, we have designed many antennas. Okay, so I'm not discussing any more on those antennas. Now I'm coming discussing a little bit about our conformal antennas. Okay. Yes, just I'm waiting that how we have designed these conformal antennas.
Yes, sir. Visible, sir.
It is visible now. Okay,
Yes, sir. Visible.
so you see, yeah, okay. So this is a conical type of antenna, okay, which is made of a copper sheet, okay, and the height of this antenna around how much? Less than a meters, okay, and so what has and you see this antenna is excited by a loop, okay. So we have excited that antenna. I mean conical structure. Actually, here the conical structure acting as a uh, uh, radiating surface, you can say, or scatterers. Okay, and our antenna is that loop. Okay, so basically, what we are observing here is that um, loop antenna, how loop antenna behave in the presence of a conductors. So how we'll solve this problem? So basically, we have solved this problem like this. Next page. I'm coming to the next page. Whether it is visible, please mention motivation here.
Yes, sir.
Yes.
Visible.
Okay. So, as I told you that conformal antenna is an antenna structure that conform to a prescribed shape. Conformal antennas are increasingly being deployed in modern aircraft, missiles, land vehicle, etc. The proposed conformal loop antenna with configuration can be particularly used as an effective and conformal radiating structure around conical front end in aerospace, vehicle, missile seeker, rockets, or high-speed automotive and rail system. It can also be used in collision avoidance system in land and airborne vehicles. In missile seeker applications, the antenna structure can also be used around missile warhead to track and obtain target information, including elevation, range, and velocity for intercepting a moving target, also missile height from the ground at close to striking a stationary target. So I'm waiting for my next page.
So it is visible, sir.
Okay, thank you. What methodology we have chosen? Okay, first we have to select the appropriate potential functions. So once we select the appropriate potential function, from there we have to calculate the electric and magnetic field expressions. Okay, from there we have to impose boundary condition on the cone and the loops. Okay, here there will be two kind of boundary condition. One we have to impose on the surface of the cone, another one we have to impose on the surface of the loop. Next, find the unknown constant in potential function in terms of a current harmonics. Actually, the potential function which we will choose will have some pardon me, unknown constant. Okay, we have to find out the value of those unknown constant. Then impose boundary condition across the delta gap voltage source. Then find the current harmonics value. Once we know the current value, okay, current harmonic value, then we can calculate each and everything. Okay, so from current expression we can calculate the input impedance, return loss, and so on. So basic thing is that you have to choose the appropriate potential function. Then you have to find out the electric field or magnetic field. Then impose the boundary condition. Then find the unknown constant. Then impose the delta gap source. Then find the current harmonics. Once you know the current harmonics, then everything will be easy. Okay, you can calculate input impedance, return loss, radiation patterns, and so on. Next slide. Is it visible?
Yes, sir. Visible, sir.
Okay, so here we have taken two potential functions. Okay, one is AR, another one FR. Okay, so each potential function have some unknown coefficient and summation from 0 to infinity. Okay, all the summation here you see in that expression, all this expression runs from 0 to infinity. And the unknown coefficient are V1, A1, V2, A2, C1, C2, D2. There are unknown coefficient for these problems. As because it is single loop, that is why here the unknown coefficient is 8. And in that expression, you will see that J nu K R. Okay, this is called Solkunov type of spherical functions. Solkunov type of spherical functions. Second one is that PMV cos theta. This is first kind of associate Legendre polynomial. First kind of associate Legendre polynomial. And sin m phi plus cos m phi is the phi variations. So we have this potential function but describing this structure. So we have to choose these things. So initially we have chosen different potential functions, but after that trial and error, we have come to the right potential functions. These are the two potential function AR and FR. One is for R less than equal to A. Okay, you see A is the radial distance from tip loop. Okay, A is the radial distance from the tip of the cone to the surface of the loop. Okay, So one condition is for R less than A, and another condition is for R greater than A. Okay. So next page, I'm waiting a little bit.
Visible, sir.
Okay, so what I have described you, just shown you in arrow, unknown constant, the spherical Bessel function, which are of Solokonov type, then the associate Legendre function, which is of first kind, then this is the harmonic equations. That is 5 variations. Now we are, okay, let it come next page.
Sir, visible, sir.
Okay, so now we are matching the boundary conditions. Okay, at boundary, that is R equals to A. Okay, the E field are continuous. So just applying that things, we are getting the below equations. So some mathematical calculation is obviously there. So I cannot show all those things. Next is the H field boundary conditions. So from H field boundary condition, we have got this kind of equations. I think it is visible.
Yes, sir.
Okay, thank you. So from there, okay, from there you see that we are imposing some, you see the excitation current. We have taken that J phi is the excitation current, some expression is there. Now applying those things, we are getting the value of those unknown coefficient, A1, A2, B1, B2, and so on. Okay. So we have calculated this value. Coming to the next page. Sorry. We are waiting little bit.
Visible,
Is it
sir.
visible? Next
Yes,
page.
sir.
That loop boundary condition. Okay.
Yes,
So from
visible.
loop boundary condition, we got D1, D2, C1, C2. Okay. Now next page. It is visible or not?
Yes, sir. Visible.
Okay. Now we are actually providing some voltage on that loop. Okay. We have taken some loop. So we are giving some voltage in that loop. So we are getting these expressions. Okay. So not discussing too much about these things. Now coming to the next page, this is our final page. I'm waiting for that current distributions. Current distributions. Please mention whether it is visible to you.
Yes, sir. Visible.
Okay. So as I told you that our intention is to get the current expression. So finally we got the current expression, that is Im. Okay. So once we know the Im, okay, then we can calculate the input impedance. Okay. You see that Zin is the Vp by summation of Im. Okay. So all these things can be calculated from here. So I'm showing some of the results here. The return loss you see. So our main target is to calculate the unknown current. Once we know the unknown current, then the input impedance, return loss, radiation pattern, all these things can be calculated. So just coming to here, so one result. I'm showing just one result. So return of the result of loop around cone. Please mention whether it is visible to you or not.
Yes, sir. Visible.
Okay, so this result is very significant. Okay, so you see that isolated loop. Okay, isolated loop means when we are not using the cone, only loop. When we are exciting only loop, the return loss is very poor. Okay, around -5 dB. Okay, that means, as I told you, discuss you in antenna miniaturization, is that any kind of small structure, small loop, okay, as because it has low resistance, okay, so it does not radiate. Okay, you see here the example, real example is here. Okay, the return loss curve minus 5 dB. It is not radiating. Okay, but when we have used the cone, okay, in the presence of the cone, you see the return loss curve, the dip is coming to minus 30 dB, minus 28 dB. So that means when we have used the conical structure, our return loss improve. Okay, and the structure radiate properly. Okay, apart from this, this is one of the advantage which we have received. Apart from this, we have received many other advantages. Okay, so as because I have given time, I think 5:15. Okay, so I'm crossing that. So I'm not
Yeah, actually,
stating this
Dr.
anymore.
Moinul Haque, Dr. Moinul Haque,
Yes, yes.
you are requested to kindly make your presentation quite a little bit compact so that we can end the session in a proper time.
Okay, okay. So I'm closing these things. Okay.
Yeah.
Dr. Aniban Karmakar, please, I'm concluding these things. Okay. So if you have any question, please ask me.
Okay. So I am asking the participants, do you have any questions? Please ask one by one.
Yes, sir. I want to ask a question, sir. First of all, the presentation was
Yes,
very
sir.
enriching and we got to learn quite a lot of things, sir. But I want to ask you, sir, if you want to strategically
Yes.
plan any antenna design, be it designing the radiator or be it designing the feed network, what are the different design equations which we can use for this purpose?
For antenna miniaturization purpose, the how will determine the resonant frequency? You are asking that questions. How will
Yes, sir.
I mean if we have a yes, yes, okay, I understand your questions. Suppose we want to design an antenna which will radiate, let's say, at 2.45 gigahertz. Okay, that is our Bluetooth applications. So how we'll choose the antenna? I mean slot length and slot width, right? This is your
Yes,
questions.
sir.
Okay,
Yes, sir.
it is answer is very simple. Yes, answer is very simple, that lambda g by 2, okay, that lambda g by 2 equals to you have to choose in such a way that coming to the back point. Okay, suppose uh, your desired frequency f is 2.45 gigahertz, right?
Right.
From there you calculate the lambda. From there you calculate the lambda.
Okay.
Okay, you can calculate the lambda c by f,
Yes, sir. Yes, sir.
right? So from
Yes,
from
sir.
from lambda you calculate the lambda g. Okay, what is lambda g? Is the guided wavelength.
Guided
Lambda
wavelength.
g
Right.
equals to lambda divided by root over of epsilon naught, right? So you
Right, sir.
got the lambda g value. Now
Okay.
lambda g by 2 will give you the slot length,
Okay. Okay.
right? You got
Okay,
my
sir.
question?
Yes, sir. Yes, sir. Yes, sir.
Then how much will be the width? How we will calculate the width? Okay, there is no such formulation is there, but one thing you will remember is that if you increase the I mean your radiating slot length too much, what will happen is that
Okay.
your cross polarization will increase. Your cross polarization in the radiation pattern will increase.
Okay.
So try to make it less as much as possible.
The slot width you are talking about, sir?
Okay, I hope that yeah, slot width, right?
Okay. 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 Okay.
Because
I get.
slot width will contribute. Okay.
Sir, the
So,
slot width will contribute to some unwanted modes to be generated that results in that cross polarization.
Yes, cross polarization, right? Because in that direction, current component will increase.
Okay.
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 We don't want those current component in that directions. Okay.
Okay.
So those
Okay.
current contribution in turns will affect our radiation pattern.
Okay. Okay. Thank you. Thank you very much, sir.
Okay.
so
Please.
I'm requesting any other participants. Do you have any questions? You can deliver. Anyone? Do you have any question? Obirup, Mr. Obirup, do you have any question? Sir, is my voice is audible?
Yes, yes, yes. I can hear you, Dr. Nivan Kormuka.
Yeah,
I can
yeah,
hear
yeah.
you.
So, so I think that, sir, no other participants don't have any question, I think. So, sir, thank you very much after all for giving your nice presentation. And the presentation is very innovative, informative, as well as very rich in technical content. So, in future, we like to request you to give
Okay,
much
thank you.
more presentation in some different other topics. And later, we will contact you and request you to give the same.
Yes.
Thank you, sir. Thank you very much.